Last time, we looked at how hierarchical clustering builds nested trees to group data. But today, we're taking a radically different approach, grouping data by its density. This map lays out our series, and you'll find algorithm number 20, DBSCAN, sitting right here in the clustering and dimensionality family. Think of a crowded city square. A cluster isn't necessarily a perfect geometric shape. It is often just a dense crowd of people. Anyone standing alone, scattered far apart from that crowd, is simply noise. Before we appreciate why that perspective matters, we have to look at the traditional alternative. The standard k-means algorithm forces you to guess the total number of clusters before you even look at the data. Worse, the math behind k-means assumes every one of those clusters is a tidy, perfectly round geometric blob. Real-world data rarely looks like a neat circle. Data points form irregular spirals, overlapping crescents, and unpredictable winding paths. Because k-means relies on that rigid geometry, it is forced to assign every single point, even the lonely ones, into a cluster. This creates a problem for anyone looking for outliers. The algorithm isn't designed to leave anything behind. That brings us to the mechanics of DBSCAN. The algorithm operates on a single insight. A cluster is nothing more than a region of high point density separated by empty gaps. To find those regions, we first define a parameter called EPS, short for epsilon. This sets a specific search radius around any single data point. Next, we set min samples. This is the strict minimum number of neighbors that must exist within that epsilon radius. Look at the leftmost section of this diagram. When those conditions are met, a point that successfully meets or exceeds the neighbor threshold within its radius is classified as a core point. This shifts the focus from the center of the entire dataset to the local neighborhood. It's the first step toward understanding the data's structure, one small piece at a time. Check the middle section. A border point doesn't have enough neighbors to be a core point, but sits safely inside a core's radius. On the right, noise is an isolated point that fails the threshold, out of reach from any core. With those definitions set, the algorithm executes its main loop. It picks an unvisited point, queries its neighborhood, and if it hits the core threshold, a brand new cluster is born. Here we see how the cluster expands. If an absorbed neighbor is also a core point, like the red points labeled A, the cluster grows organically, chaining overlapping neighborhoods together. Chaining halts at border edges, leaving solitary points, like the blue N, entirely untouched. By chaining these local, dense neighborhoods together, DBSCAN automatically discovers the final cluster count and shape. You don't have to guess the numbers. The data reveals them. Let's look at the half-moons dataset. On the left, standard k-means fails, slicing a vertical line right through the crescents. But on the right, DBSCAN follows the density of each curve, successfully flagging the stray red anomaly off to the side. In this visual, we see the results of this logic. DBSCAN isolates completely different shapes, a round blue blob and a winding green ribbon, keeping them cleanly separated from the scattered gray noise points. This dual capability is what makes the algorithm so effective. It follows the natural flow of these clusters, keeping anomalies clearly separated in the empty space. Now, let's open our Python notebook. We'll see exactly how epsilon and min samples are implemented in the code to find real clusters. This graphic shows our make-moons testing ground, two interleaving crescents with scattered noise. On the left, traditional algorithms like k-means fail this stress test, illustrated by the red dashed straight cut line, because they assume clusters are perfectly round blobs. To solve this, we import the DBSCAN class. This allows us to access a highly complex density evaluation engine without having to write all the underlying math from scratch. By setting up a geometric layout that straight lines and perfect circles cannot solve, we prove exactly why a density-based tool is required to extract the actual structure of this dataset. The entire clustering process happens in a single line of execution. We define a variable db, call DBSCAN, and feed it two specific arguments, EPS set to 0.1 and min samples set to 5. That first parameter, EPS, is our neighborhood radius. Think of it as a strict geometric boundary, expanding outward from any given data point by exactly 0.1 units. The second parameter, min samples, acts as a density threshold. For that central point to be recognized as a valid core anchor of a cluster, it must capture at least 5 distinct data points inside that 0.1 radius ring. Appending .fitx at the end is what starts the engine. It commands the script to perform this exact radius and threshold check across every single data point in our MakeMoons dataset. The most important part of this code is actually what's missing. Because the clusters emerge naturally from the data's own density, we never had to input an expected cluster count. To read the results, we check the variable db.labels_. The algorithm outputs an array assigning a specific integer to every processed data point, matching it to a cluster family. Points labeled 0 belong to the first cluster, and points labeled 1 belong to the second. Notice the -1 value scattered in the array. In DBSCAN, -1 is the explicit tag for an outlier. It means that point failed the density check and couldn't be connected to any core cluster. By counting the distinct non-negative integers, the zeros and the ones, and completely ignoring the negative ones, the algorithm returns a final, accurate cluster count of 2. This labeling convention does dual duty. By isolating unbound data with a -1, DBSCAN inherently acts as a free anomaly detection system, cleanly separating valid crescents from background noise. You can verify this exact execution syntax yourself in the open-source notebook located at this GitHub URL. When you run it, you'll see that EPS and min samples are the only 2 tuning dials you have to control how the algorithm behaves. Set the EPS radius too small, and the density requirement fails. The crescent structures shatter into a spray of -1 outlier points. Conversely, crank the dial too high, and overlapping search rings cause the 2 crescents to bleed together into a single useless blob. This extreme sensitivity to tuning those 2 parameters is the necessary trade-off. It's the cost of admission for an algorithm that maps arbitrary shapes without requiring you to guess the final cluster count up front. So where does a tool with this much shape-finding power, yet this much parameter sensitivity, actually earn its keep in real-world scenarios? And under exactly what conditions does it quietly break down? Scatterplot shows exactly how the algorithm treats a raw dataset. While colored points group into organic shapes, the algorithm isolates scattered gray points at the fringes. In fraud detection, those unclustered gray dots are the primary target, isolating highly suspicious, standalone transactions. The utility of this approach lies in its exclusions. By strictly defining what constitutes a dense, normal group, the math automatically flags the outliers. This map-based simulation illustrates how spatial coordinates translate into physical boundaries. Whether you are mapping taxi hotspots, clustering crime reports, or tracing the sprawling edge of a wildfire along a ridgeline, natural phenomena form irregular organic shapes. Engineers also apply this logic to image segmentation. The algorithm groups pixels together by simultaneously calculating their physical proximity to each other and the density of their color values. It also serves as a necessary frontline filter. When processing raw, chaotic inputs from physical sensors, a density check drops erroneous, standalone data spikes before they corrupt downstream machine learning models. Physical spaces and sensor outputs yield messy datasets. Processing them requires a tool that follows the actual concentration of the data rather than assuming it fits into neat geometric circles. This slide breaks down the operational advantages. Starting in the orange box, there is no need to pick K up front. It discovers the final number of clusters organically. Scanning up, it maps arbitrary shapes, like moons or spirals, by following contiguous density, while actively discarding sparse points as noise. The math is highly deterministic. If you run the algorithm multiple times over the exact same dataset, you get the exact same clusters, avoiding the unpredictable variations common in tools that rely on random initial starting points. Combine those traits, and you have a highly reliable system. As long as your data maintains a consistent physical structure, you can deploy the logic and let it run. But that reliance on consistent structure introduces a rigid limitation. This diagram shows an extremely tight cluster next to a loosely packed one. When applying a single density radius across the entire set, it perfectly maps the dense group, but completely misses connections in the sparse one. Because it requires a fixed minimum of points, optimizing for dense neighborhoods inevitably shatters the sparse ones into isolated dots. The second failure state occurs in high-dimensional datasets. When plotting data across hundreds of features, the mathematical distance between points begins to equalize. Look back at the performance chart, specifically the top center red box. As those spatial distances blur, the concept of a dense neighborhood breaks down, dragging the compute time into a worst-case scenario of O of n squared. To fix these gaps in a production pipeline, engineers swap in tools like DBSCAN or optics, which dynamically adjust to varying densities. Or, if the data actually does form strictly round, balanced groups, they revert to standard k-means. DBSCAN is a specialized tool. Applying it to data with wildly shifting densities or feeding it ultra-high dimensional arrays guarantees a systemic mathematical failure. This visual grid categorizes the essential formulas of computer science. You can see DBSCAN right here, sitting at position number 20 under the Clustering and Dimensionality block. This organizational framework comes from Imran Amran's 50 algorithms every programmer should know. You can find the companion code in his GitHub repository and explore the complete visual breakdowns over at neuralsca. DBSCAN reframed clustering around a single human instinct. A crowd is a crowd, and a loner is a loner. No K, any shape, outliers for free. That is why, nearly 30 years on, it is still one of the most used clustering algorithms in the world.